Okay, well, here we go. Since I couldn't be here today, we're going to be recording the notes for today as we get into our energy and states of matter unit. Yesterday, we wrapped up the results of the Icy Hot Lab, where we looked at heating curves and cooling curves to show how the addition or subtraction of energy alters the state of matter or the temperature. One of the ways that we track this and model those changes as we look at physical states of change for different samples of matter is through the use of energy bar charts. And so this is going to be our first way to model this as we work through the unit on energy and states of matter. And so constructing an energy bar chart, if we look at the example that's listed here, a cup of hot coffee cools as it sits on the table. So this is something I deal with every day. I pour my coffee in the morning and it's nice and hot, and then 20 minutes later, it's ice cold, or at least room temperature. So we do energy bar charts, which we affectionately call LOL diagrams, because if you look at the axes for the initial and the final, they make like little L's, and then in the center, we have this circle, which represents the system that we're analyzing, the O in the middle, so energy bar charts or LOL diagrams. So we have an initial state and a final state. So what is the energy state for our sample of matter before any energy change takes place, and then what is the energy at the end? Across the top of each one, we have ETH, which represents our thermal energy, EI, which represents our interaction energy, and ECH, which represents our chemical energy. In between the two, we have our energy flow. So the circle I said represents the system. And for our example one here, we're looking at a cup of coffee. And so that is going to be our system. So we're going to look at energy. Is it moving in or moving out in this scenario? And then as it does, what amount of energy do we have for our three categories here at the end? So the system, the cup of coffee, is the only thing that we're tracking the energy of in this energy bar chart. When we are going through other examples, the first thing we need to do is identify what is the system so we know specifically what it is that we are looking at tracking the energy of. Anything that is not a part of the system makes up the surroundings. And so there's a lot of things that make up the surroundings. If you think about all of existence, that cup of coffee is a very small piece of it. So we're only looking at that tiny little bit of energy. Everything else is on the outside of it. Now, when we talk about energy and energy transfer, we also have to talk about the total energy of the universe. The total energy of the universe is a constant. It's a fixed amount, kind of like the law of conservation of mass. There's a fixed amount of mass in the universe, and so it only goes through those changes like we talked about back in Unit 1. Here, the total energy of the universe is constant. So if we think about the total amount of energy that is available throughout the entire universe, that would be equal to the energy of our system. So that small, tiny sliver of the universe, that's the part that we're analyzing. Everything else, all the other energy in the universe, is a part of these surroundings. This idea is known as the law of conservation of energy. So similar to the law of conservation of mass, where the total amount of mass is fixed, it can only undergo changes. Here, the same thing is true for energy. The total amount of energy in the whole universe is a constant. And so if we have energy being added to our system, it has to come from the surroundings. If we have energy being lost by the system, it has to be going into the surroundings in order to maintain that constant level. So as far as working with the energy bar chart, once we have it set up and we've identified the system, then we need to decide whether or not chemical energy is involved. Well, this system that we're looking at, the cup of coffee, at the beginning, it's a cup of coffee, and at the end, it's still a cup of coffee. It's not as hot as it used to be, but it also hasn't turned into something different, which means we can ignore chemical energy for now. Why? Because chemical energy only changes during a chemical change. We're not talking about chemical change yet. Right now, everything that we're talking about in this unit, energy and states of matter, only physical changes. Later in the year, when we get into chemical change more heavily, then we'll be looking at energy bar charts and how the chemical energy changes. But for now, we can ignore it. It's going to be blank the whole time. If it's not changing, there's no reason to put that in there for us to look at. We're just going to focus on thermal and interaction energies. So in doing the energy bar charts, the first thing that we can put bars in for is interaction energy. The amount of interaction energy that we have is going to be based on what state of matter we are looking at. Now, again, as we've been talking about, interaction energy is due to interactions between the particles. The energy stored due to the arrangement of particles is ranked as solids having the least amount of interaction energy. Liquids having more, because as we saw in the lab, you have to have the sample of matter absorb energy in order for it to transition from solid to liquid or liquid to gas. So liquid would have more interaction energy. And then gases would have to have even more interaction energy to be able to transition from liquid to gas. So for our bar charts, and again, this is really more of a qualitative representation as opposed to quantitative. We simply choose to say, if we have a solid, that's going to be 1 bar of interaction energy. Liquids get 2 bars and gases get 4 bars. The values here are scaled to show the interaction energy requirements for the phase change, meaning it takes a certain amount of energy to transition a substance from solid to liquid, but it takes more energy to transition a substance from liquid to gas. So it's not necessarily that it takes twice as much energy to turn a liquid into a gas, but it definitely takes a lot more. And next week, when we start to get into more of the quantitative analysis, we'll see some of those values and we'll see why we have 4 bars for gases and 2 bars for liquids. An increase in interaction energy is required to overcome the attractions between particles. This was one of the things that we talked about coming out of the icy hot lab. When we melted the ice and it went from solid to liquid, we had to add energy, increase the interaction energy to overcome those attractions and pull the particles far enough apart that they could start moving past each other. And then when it got to a boil, we had to be putting in a lot of energy in order to get those particles to completely separate from each other to go into the gas phase. So interaction energy always changes when the phase of matter changes. If it goes from solid to liquid, liquid to gas, or vice versa. So for our example here with the cup of hot coffee that cools down, we're going to start with 2 bars because initially the cup of coffee has a liquid, the coffee's a liquid. And after it cools down, it's still a liquid. So the interaction energy here has not changed. It was a liquid to begin with, it's a liquid at the end, so 2 bars and 2 bars. And then as far as thermal energy is going to be connected to the temperature. When particles move faster, they have more energy, therefore their total energy changes and the thermal energy is being affected. So to represent the hot coffee, I have chosen to go with 4 bars. That's just what I chose. As it cools down, the temperature is going to be dropping, so the thermal energy, the total energy of the particles is going to drop, and now it's down to 2 bars. Now, as I made a note here, the number of bars only needs to show how energy changed. I could have had 3 bars and gone down to 2. It's fine. We just need to show that the thermal energy decreased. So other values might also work, but you should try to be kind of consistent in your representations so that you get used to what they should look like. So finally, we've gone from the initial condition where we have 4 bars of thermal, 2 bars of interaction. That was 6 bars of total energy in that cup of hot coffee. Over time, though, the temperature went down. So we showed that by going down to 2 bars of thermal energy and then still 2 bars of interaction energy. So we have 4 bars at the end. That means that our cup of hot coffee lost 2 bars worth of energy. Well, where does that energy go? Well, again, if the system loses energy, then the energy has to leave that system and go off into the surroundings. And so you notice here in the center of the diagram, we have 2 bars of energy with an arrow leaving the system. And next to it, we have the letter Q. 2 bars of energy left the system and entered the surroundings via heating. That Q is the shorthand notation, the symbol that represents the process of heating. Why isn't the letter H? There's a big, long explanation for that. I can tell you when I'm there in person, but just know that the letter Q is used to represent how the energy was leaving the system. Heating, like we talked about last week, Heating is the transfer of energy by collision of particles. So you had the hot coffee particles, the hot coffee cup. Those particles were vibrating very quickly, moving quickly, hitting the cooler surrounding air, transferring energy to it. The air particles heat up, the coffee particles slow down, hence the changes that we see there. So this is the complete energy bar diagram for that cup of coffee cooling down. Now, what if we do have a phase change? So we have a new example here. Tray of ice cubes at -8 degrees Celsius is placed on the counter and becomes water at room temperature. Uh-oh, somebody left the tray of ice cubes sitting on the counter. So what do we know about the system, or about the situation? First off, the system is the tray of ice cubes. So that's what we're looking at. That's what we're going to be considering the energy of. We also know that solid water turns into liquid water. That's a physical change, so no chemical energy change is necessary. Again, we're going to be ignoring that in all these examples. We know the interaction energy changes because we went from solid to liquid. So if you have a phase change, interaction energy changes. We also know the thermal energy has to change because the temperature went from -8 to room temperature, which is about 20 degrees Celsius. So what would that look like in our energy bar charts? Well, we'd start by putting the ice tray in our center circle to show that that is our system. And then we could put in 1 bar of interaction energy because it's a solid. And I put half a bar of thermal energy here because this is very, very cold. Again, it doesn't have to be whole numbers of bars. We could put 1 bar there, but to symbolize that it's very cold, low thermal energy, half a bar. Afterwards, we know that it's turned into a liquid. So the interaction energy needs to be 2 bars. For thermal energy, it also is now at 2 bars, showing that the thermal energy increased because the temperature increased. So we can see from the initial to the final, this system has gained energy. And so now energy was absorbed by the tray of ice from the surroundings, and once again, via heating. That ice tray was cold, was in warm air on a warm counter. The vibrations and the motion of those warm air particles were colliding with the ice, speeding up those ice particles, absorbing that energy. Overall, we gained 2.5 bars of energy via heating. So again, that Q. So we can see the energy going into the system, hence why in the final, the energy is increasing. Okay, I had to find my notes here for these example problems. So at this point now, we've completed the notes in the note packet, and we're going to look at Energy and States of Matter Worksheet 1. It says at the top, diagramming energy change for state of matter changes, and then there's a big bold word there. It says notes. This is just some example problems to do some other examples. Okay, number 1, a cup of hot coffee cools as it sits on the table. That should sound familiar. That was one of the ones that we just did in our notes. So once again, what did we have for our system there? Well, it was the coffee. And it's a cup of hot coffee, which means the coffee is liquid. So that is automatically 2 bars of interaction energy. And because it's really hot, we're going to go 4 bars. Again, it doesn't have to be 4 bars. You could go with 3 if you want. All we need to show here is that at the end, the energy is decreasing. So as the coffee cools down, it's going to decrease in thermal energy, but it's still a liquid. And so we have 2 bars there. So once again, we go from having 6 bars to 4 bars, which means we had 2 bars that left the system. And how did it leave the system? Via heating. Once again, those hot particles were moving faster than the surrounding particles, transferred energy out, and we saw the decrease in thermal energy for our cup of coffee. For question number 2, now we take a can of cold soda out and leave it on the counter. And so it's going to be getting warmer as it sits on that counter. Our system is our can of soda. And the can of soda, when it comes out of the fridge, it's going to be a liquid. The soda is a liquid in there. And after it warms up, it's still going to be a liquid. So 2 bars of interaction energy at the start and final. Now when it comes out of the fridge, it's going to be nice and cold. And so we'll have low thermal energy. So I put that as 1 bar. Again, I'm just arbitrarily choosing that. And as it sits on the counter, it warms up. We want to show the thermal energy increasing because the temperature increases. So I'm going to switch that to 2 bars of thermal energy. So once again, we look at our total bars. We had 3 bars at the start, 4 bars at the end. So did our system gain or lose energy? Energy went up, we gained energy. So I got my 1 bar. Energy is going into the system. How? Via heating. Example number 3, a tray of water at 20 degrees Celsius is placed in the freezer and turns into ice cubes. So this is kind of the reverse of what we saw from that one example earlier in the notes. So that tray of ice cubes, before it goes, that tray of water starts as a liquid, so we got 2 bars of interaction energy. But as it sits in the freezer, it's going to turn into a solid, so it's going to lose some interaction energy as it goes to the solid state, so 1 bar for solid. Room temperature, I'm going to put 2 bars for my thermal energy. Again, I'm just choosing that. The temperature is going to be dropping, so what am I going to do for my thermal energy? I'm going to have less. And so again, because it's getting to be so cold, I'm going to put half a bar in there. And so where we started with 4 bars, and at the end we only have 1.5 bars, that means that we lost 2.5 bars once again via heating. That energy leaves and goes into the surroundings. Now it says down here, question 4, if you turn over your note sheet, question 4 says, where does the energy that leaves the system in number 3 go? How does this energy transfer affect the room temperature in the kitchen? Do you have any experience that supports your answers? Well, we talked about this in class last week or the week before. A freezer is really a heat mover. Okay, it's an energy mover. So that energy that's lost by the tray of water gets absorbed by the freezer and then puts that energy out into the kitchen or whatever room the freezer is being kept in. So we talked about how if you put your hand near the back of a refrigerator or around a freezer, wherever the condensing unit is, it's usually on the bottom or close to the ground in most modern appliances, you're going to feel some really warm air. That warm air is being caused by the energy that was lost by, in this case, the tray of water as it freezes. That energy leaves the water, gets transferred out into the room. The room is absorbing that energy that was lost, increases the temperature slightly, and makes the surrounding room a little bit warmer. The last example here for today is question 5. On the ice cubes described, or one of the ice cubes described in number 3, is placed in a glass of room temperature soft drink. Do separate bar charts for the ice cube and the soft drink. Okay, so we'll take our ice cube and we'll make that the top one, and then we'll make the soft drink the bottom example here. So for the ice cube, it starts out as a solid, and it's going to be pretty cold as it comes out of the freezer. This time I'm going to use 1 bar. And then as it sits in the drink, the ice cube is going to stick around for a while, so we'll say it's still a solid. But over time, it is going to be absorbing some energy, and so we're going to see a little bit of increase in the thermal energy of it. Okay. So that really cold ice cube is warming up, but it hasn't melted yet. And so at this point, we'll do the energy flow here in just a second. For the soft drink, so the soft drink is a liquid, and it's going to stay a liquid as we go to drink it. Initially, it's warm when we first take it out of, I don't know if it's like a soda, if we take it out of the 24 pack of soda. And then by putting the ice cube into it, that's going to lower the temperature of the soft drink. And so we'll have that go down. Now, as we do that, we see for the soft drink, we started with 5 bars, and we ended with 4 bars. which means our soft drink lost 1 bar of energy. Its overall energy went down, it got cooler, and it gave that energy away. But where did that energy go in this instance? What caused the soft drink's energy to go down? Well, it was the ice cube. For our ice cube, we had 2 bars to start, and at the end, it warmed up and went to 3 bars. So it gained 1 bar of energy. The soft drink lost energy because of the ice cube, while the ice cube gained that energy. So we had the transference of energy between the soda and the ice cube. And this is what happens when you put ice cubes into a beverage to make it colder. You reduce the thermal energy of the beverage, and that energy increases the thermal energy of the ice cube. Now, if you leave the ice cubes in there long enough, they will continue to absorb energy from the soft drink. The thermal energy will go up, the ice cube will melt, and then you have no more ice cube. That water will just then be absorbed into the soft drink. So, shows a really good law of conservation of energy. The energy lost here by the soft drink is absorbed by the ice cube. Okay, so that is it for the video here. We had the notes in the note packet. We had 4 examples of energy bar charts here along with the explanations. Your assignment for tomorrow is to work on Energy and States of Matter Worksheet 2, all of the questions there. Notice at the top of that assignment, highlighted in yellow, besides doing the energy bar charts, I do want an explanation to go along with those about what's going on. So please work on that for tomorrow. You will be creating whiteboards and presenting your solutions in class, and I will see you when I see you.